Bismillahirrahmanirrahim. We are starting the new session and continuing with the solution of linear PDEs. Our focus in this session will be on the questions where only one pair is possible to solve out of three. Then we will see that how we can find the solution of second pair, because as I said that it is mandatory to solve two pairs to prove the auxiliary equation. So starting with example number 1. In example number 1 we have P plus 3Q is equal to 5Z plus tangent Y minus 3X. Let's consider that this is the case. So this is equation number 1 and again it is in its standard form. So here capital P is equal to 1, capital Q is equal to 3 and capital R is equal to 5Z plus tangent Y minus 3X. Look in this example, P and Q both are constants. So it doesn't matter whether P and Q holds any values. P, Q and R, all three can hold any values. And capital R is holding this complete value. Because I said whatever will be on the right hand side will be treated as capital R. So writing auxiliary equation, it means dx over 1 equal to dy over 3 equal to dz over 5z plus tangent y minus 3x. So this becomes equation number 2. Now making pairs. So pair number 1 is dx over 1 equal to dy over 3. Pair number 2, dx over 3 is equal to dz over 5z plus tangent y minus 3x. And then finally pair number 3, that is dx over 1 equal to dz over 5z plus tangent y minus 3x. So now it's time to go and check that any simplification is possible or not. There is no need of any simplification. Here no simplification is possible and here also no simplification is possible. So it's time to check that which pairs are possible to solve. Here z is missing in the denominator and z is also not there in the denominator, so this pair is possible to solve. Here in numerator y is missing and in denominator y is there and it is not possible to eliminate this y, so this pair is not solvable. And here I made a mistake here. This is dx over 1 and here it is dy over 3. So dx and then dy dz dz. Yes. So here y is missing and we cannot eliminate this y. Here look, x is missing in the numerator and it is not possible to eliminate this x, so this pair is not solved. So look, only one pair is possible in this scenario. So how we will proceed? Whichever pair is possible to solve, just solve it. So I write p dx is equal to dy, cross multiply, then integrate. So I got 3x is equal to y plus c1 and then finding the value of c1, so it means 3x minus y equal to c1. So now we solve this pair. Now how we can solve the second pair? It is up to you. First decide which pair you want to solve. Which pair you want to solve? Let's say I want to solve this pair. You can apply the same technique on this pair as well. And I recommend you to try this one. I am trying to solve this pair. So look, this pair will be solvable if I am able to eliminate 3x x from here. So it is possible to eliminate x. If I can check, I can get the value of 3x from here. It is y plus c1. So if I substitute this value here, it becomes dy over 3 equal to dz over 5z plus tangent y minus y plus c1. In place of 3x, I write y plus c1. You can do same thing for this pair. What will be done? Since y is not there and y is here, so just take the value of y from here and substitute here. Just take, as I take the value of x, just take the value of y from here and substitute here, then this pair will also be able to solve. So if I simplify this denominator, this will be equal to dz over 5z minus tangent c1, because y cancel with y. And now look at this one. No x is there in the denominator. c1 is constant. So no x is there. It simply means now it is possible to integrate. This is also the case of separable variable. So I directly integrate. So this will become y upon 3 equal to 1 upon 5 log of 5z minus tangent c1 plus c2. Because the derivative of denominator is just 5, so I divide it with y 5, and it means y upon 3 is minus 1 upon 5 log of 5z minus tangent c1 equal to c2. So the answer of c2 is there. As soon as you make the answer of c2, just back substitute the value of c1. c1 was equal to 3x minus y. So just write 3x minus y instead of c1, and this will give you the answer of c2. So final answer will be phi of 3x minus y and y upon 3 minus 1 upon 5 log of 5z minus tangent 3x minus y equal to 0. So look, we made all pairs solvable by the help of this substitution. So let us take more examples on the same technique. Example number 2. xyp plus y square q equal to xyz minus 2 square, 2x square. This is example number 2. Again, in its standard form, capital P is xy, capital Q is y square, and capital R is xyz minus 2x square. So writing down the auxiliary equation, So auxiliary equation will be dx over xy equal to dy over y square equal to dz over xyz minus 2x square, equation number 2. Now time to make pairs. Dx over xy equal to dy over y square, pair number 1. Then dy over y square equal to dz over xyz minus 2x square. And pair number 3, dx over xy equal to dz over xyz minus 2x square. It's time to check for simplification. I can cancel this y with this one. So remaining I have dx over x is equal to dy over y. Here no simplification is possible. Here no simplification is, here yes simplification is possible. That is dx over xy equal to dz over, if I take x common, this is yz minus 2x, so I cancel x with x. Now look all these pairs and check that whether all 3 or any 2 or any 1 is possible to solve. Here look, z is missing from denominator, z is also missing from numerator, so this possibility is solvable. Here x is missing from numerator and x is there in the denominator, and we are not in a position to cancel x, so this possibility is not solvable. Here what is remained? Dx over y equal to dz over yz minus 2x. Since y is missing from the numerator, it is not possible to cancel y from the denominator, so this possibility is also not solvable. So what we decided, that whichever possibility is possible to solve, just solve it. So this will, if I integrate, this will become log x equal to log y plus log of c1. As I told you previously, do write log with constant of integration, so it makes your later on calculation much more easier. So I have log of xy is equal to log of c1. It means x upon y equal to c1. Now you need to decide that which pair you want to solve, this pair or this pair. It is up to you. Whatever you will decide, it is possible for you to do. In previous example I solved this one, so in this example let us try to solve this pair, this one. So in this one, which term is not required? We do not require x in the denominator. So just take the value of x from here. X will be equal to y c1. So substitute x on that place. So we get dy upon y square equal to dz upon, I write y c1 into yz minus 2 y square and c1 square, because x square is there. Now try to simplify it. So dy upon y square equal to dz upon y square, c1 is common. So what is remaining? Z minus 2c1. Now we can cancel y square with this y square. So what will be remaining outcome? The remaining thing will be dy over 1 equal to dz over c1 z minus 2c1. And now there is no x left in the denominator. So now this pair is also solvable, and it is also in the form of separable variable. So just integrate. So if I integrate this one, on left hand side I will have y, and on right hand side I need to write 1 upon C1 log of C1 z minus 2C1, because the derivative of denominator is C1, and then we need to write C. Now we integrate it. So as soon as we integrate it, it's time to back substitute the value of C1, and C1 was equal to x upon y. So I write y is equal to 1 upon x upon y into log of x upon y z minus 2x upon y plus C2. So if you made a little bit simplification, then I can cancel this y with this y. So x will minus x minus log of x upon y z minus 2x upon y is equal to C2. And hence we can write the final answer as, therefore phi of x upon y and x minus log of x upon y z minus 2x upon y equal to 0. This will be the final answer of this example. So I did not solve this pair. If you find that this pair is more easier to solve, then I said that it is possible to solve any one of pair, whichever you want, you solve that particular pair. So this concludes with the second example. Let me give you one more example of this. So you have enough practice for this. So now we are considering third example. Example number 3. Example 3. Z square plus xy px minus qy is equal to x power 4. If you look at this example carefully, you will be able to notice that this is not in its standard form, because on left hand side we need two terms. This is the case of a single term, in which we can easily find the coefficient of small p and coefficient of small q. And as I told you that I will share with you few examples in which the given equation will not be in its standard form. So there are two possibilities to convert this equation into its standard form, and I will discuss both possibilities with you. There is no difference in both possibilities. Look at possibility number 1. I write this in this way: px minus qy is equal to x power 4 upon z square plus xy. I remove this whole term on the right hand side. And look, now this equation is in its standard form. Here capital P is x capital Q is minus y and capital R is x power 4 upon z, z square plus xy. The second method was this one. Move this z inside this. So this will be z square plus xy and zxp minus zyq is equal to x power 4, and then open this bracket, z square plus xy zxp minus z square plus xy zyq is equal to x power 4. Now again this is in its standard form, because here capital P is z square plus xy into zx, capital Q is minus z square plus xy into zy, and capital R is x power 4. If I do in this manner, the auxiliary equation will be dx over x equal to dy over minus y equal to dz over x power 4 upon z, z square plus xy. In this scenario, the auxiliary equation will be dx over z square plus xy zx equal to dy over minus z square plus xy zy and dz over x power 4. I am doing in both ways so you can understand, then there is no difference in doing either in this way or in this way if you are not making any calculation error. Both questions will merge on the same position. Look here, if I make the three possible pairs, the pair number 1 dx over x equal to dy over minus y. Then pair number 2 will be dy over minus y equal to dz over x power 4 z, z square plus xy. And then pair number 3 will be dx over x equal to dz over z, dz over x power 4 upon z, z square plus xy. If you look on this side, again there are three possible pairs are possible to make. Pair number 1 will be dx over z square plus xy zx equal to dy over minus z square plus xy zy. This is pair number 1. Then pair number 2 will be dx over z square plus xy zx equal to dz over x power 4. And then pair number 3 and then pair number 3 I am writing pair number 3 here, that is dy over minus z square plus xy zy equal to dz over x power 4. Now coming back on the method 1 technique. Here, look, z is missing from the numerator, z is also missing from the denominator, so this pair is possible to solve. Here, x is missing from the numerator and not possible to eliminate x from here, so not possible to solve. Here, y is missing from the numerator and it is not possible to eliminate y from the denominator, so not possible to solve. So pair 1 was solvable. And if you look at this example, if I simplify this one, this whole will cancel with the whole, z will cancel with z, and I end up with dx over x equal to dy over minus y. Look at the same one. And again, this is possible to solve. So when you reach at this point, you will end up that both will become the same questions. There is no difference in solving this way or that way. So that is why I solved till here in both ways, that if you do your simplification either this way or that way, it will not hurt the final conclusion. If you do not make any error, it will not hurt your final conclusion. So now moving on to solve, to complete the solution of this one. So now we are solving this pair. So this is log of x equal to minus log of y plus log of c1. So it means log of x plus log of y is equal to log of c1. Log of xy is equal to log of c1. Log cancel with log. So xy is equal to c. And let me decide that we will solve this pair. So we need to eliminate y from here. Y from here, we need to eliminate y from here if we want to solve this pair. So the value of y is y equal to c1 upon x. So substituting here the value of y, it will become dx over x is equal to dz over z square plus x power 4 upon z square plus xy, y is equal to c1 upon x. So I can cancel this x with this, remain x cube, and this x with this x. So on simplification, I will get dx is equal to z square plus c1 upon x cube into dz. And then if I move x cube here, this becomes x cube dx is equal to z cube plus zc1 dz. Now we can easily integrate this term, and I will show your integration on this side. I am showing this integration here. So on integration, I will have here x power 4 upon 4 equal to z power 4 upon 4 plus z square by 2c1 plus c2. Then x power 4 by 4 minus z power 4 by 4 minus z square by 2c1 is equal to c2. Back substituting the value of c1, x power 4 upon 4 minus z power 4 upon 4 minus z square by 2, and c1 was equal to xy. So it is C2. Hence final answer will be phi of xy and x power 4 upon 4 minus z power 4 upon 4 minus z square by 2xy equal to 0. So this is the way when you have only one pair is possible to solve. So now it's time to write few practice problems for you to have practice on this as well. So now here I am writing few practice problems for you before the end of this session. So practice problems. Number 1, xzp plus yzq is equal to xy. Number 2, p minus q is equal to z upon x plus y. Number 3, p minus 2q is equal to 3x square into sine y plus 2x. Number 4, xy square p minus y cube q plus axz equal to 0. Number 5, x square minus y square minus z square p plus 2xy cube is equal to 2xz. So I write few examples for you. These examples are belonging to the property that when only one pair is possible to solve. So this concludes this session, and we will continue with this solution of PDE in the next session inshallah. So it's goodbye from now.